However, alternative formulation of density functional theory, which uses ensemble representation for the densities, can operate both with ground and excited states, and their existence of the Kohn-Sham potential or exchange correlation potential has been rigorously proved. And this is big advantage of ensemble DFT before the Kohn-Sham DFT from the formal standpoint, formal point of view. So what is, I very briefly outline what are the ideas behind ensemble DFT. Basically, this is the same as multi-configurational representation of the wave function in the wave function theory. Only now we operate with densities. So the statement that was proved by many researchers, basically say 40 years ago, it began. Formal statement was that any physical density can be mapped onto ensemble density. Any physical density, fermionic density in this case. That is important because bosons, they don't care about all these tricks. Fermions are very individualistic. They sit in different, they should have all different, say quantum numbers sit in different states, but bosons feel comfortable in the same quantum state. Like if we had orbitals, then all bosons could be sitting in one and the same orbital, no matter how many bosons there would be. But fermions are different. And any physical density of fermions, of electrons, electronic density, can be mapped onto ensemble density. Ensemble density is simply average with some coefficients of densities of components of the ensemble. So this is, so far, this is very formal, formal statement. And exact functional form was derived by Elliott-Leib, so in 1983, and it corresponds to the same expression, formal expression, only with internal energy, or in this case, this will be Helmholtz energy from thermodynamic point of view of electrons, of the, say, ensemble components. Later, in the end of 80s, the concept of ensemble DFT, this was formulated first for the ground state, and later it was extended to the excited state, where variational principle for ensembles of ground and excited states was proved by Gross, Oliveira, and Kohn, in the sense that if we take some weighted sum of energies of several states, ground and several excited states, combine them into one ensemble with fixed weights, then, and variationally optimize it, then this average energy will be always above the average energy of the exact solutions of the Schrödinger equation. Right? So this is the essence of the variational principle. So if we take now these trial wave functions, whatever type, we can say freely optimize them, and we'll never fall below the exact value.
Is that you optimize the coefficients omega here?
No, omega here omega are fixed.
Oh, okay.
Yeah, in this case.
I see.
Well, and this is basis for variational formulation of density functional theory for excited states. It should be not a single state, but several states, ground and some excited states included into the ensemble. And in this way, we can define these energies of individual components variationally. So we can apply the variational theory.
So the omega is a fixed for all states.
Yes, right. Here, omegas are fixed. There, they may be not. Well, formalities have been derived, as I said, in the very important work by Elliott-Leib, where the most important statement was this theorem that essentially proves the validity of these two representations. What's important, the same coefficients. Here we use the same coefficients for components of the ensemble. Right, Elliott-Leib has proven this equation in his important work, and later the existence of the functional and its differentiability was proved by two German scientists with the name English, which doesn't mean English, but let's say angel is angel, say angel. Angel is angel in German, right? So they are two angels.
Angel.
And they have proven differentiability of this density functional, of the ensemble density functional. So
adiabatic connection here, do you?
They did not use adiabatic connection, strictly speaking. However, adiabatic connection was used later by some other researchers. As I remember, Morrison used adiabatic connection to demonstrate that single determinant approximation, single determinant representation of the density is not valid for some atoms. For example, for beryllium-like atomic systems. This is famous atomic systems because 2s and 2p orbitals, depending on the nuclear charge, in the limit of large nuclear charge, they become degenerate, s and p orbitals, and therefore beryllium has some gap between 2s and 2p orbitals and doubly occupied 2s orbital. But as we increase the nuclear charge, for example, go into atomic ions, cations, then p orbitals become closer and closer to 2s orbitals, and they become degenerate. And in this case, one needs to switch to ensemble description of the systems, which leads to, in fact, to fractional occupation numbers of the respective Kohn-Sham orbitals. What has been found in numeric simulations, and these were first principles numeric simulations, attempts to reconstruct the Kohn-Sham potential for this simple representation of the Kohn-Sham orbitals. So if we have known density ρ, obtained, for example, from high-level wave function calculations with nearly full CI quality, for example, the density ρ, we can try and reconstruct the respective Kohn-Sham orbitals and the respective Kohn-Sham potential. And what was found in these works, that for some systems, yes, indeed, we can end up with a single Slater determinant with all orbitals below a certain level doubly occupied. But for other systems, in particular for methylene molecule or maybe for C2 molecule, for that rectangular H2 plus H2 problem, it was found by the Barnes group that simple single determinant representation leads to occurrence of the hole below the Fermi level, so empty orbital below occupied, which means that this is not a ground state, and therefore it is not valid to describe it by the density function, by the standard density functional theory, such a configuration. So what they try to do, they try to apply strict Kohn-Sham method without knowing the exact potential, but they try to find it from the known density, and they ended up in a situation where the Kohn-Sham method was not valid for some molecules. In particular, they used these molecules, and these molecules from wave function point of view are characterized by multi-configurational wave functions, such as beryllium-like atomic systems. They also have the same difficulty. So either one needs to abandon the, say, Hohenberg-Kohn theorem and therefore Kohn-Sham methodology for these specific systems, or one needs to switch to fractional orbital occupation numbers. So fractional orbital occupation numbers, in this case, originate from mixing between several configurations or components of ensemble. So each component has fixed occupation numbers, and each component, well, there may be continuously occupied orbitals, like corresponding to the Aufbau principle or build-up principle. So all orbitals below a certain level are doubly occupied, or they may be not corresponding to this. This will correspond to the excited state from this configuration, right? And remember that there was formulation by Gross-Oliveira-Kohn, who proved that for linear combination weighted sum of these two configurations, the variational principle is valid. So one can use these densities of these and that determinants to construct some sort of multi-determinant representation for the density of certain ensemble. And then if one requires that the density of this ensemble is exactly the same as the density of exact physical system that we obtained from high level, let's say CI problem, solution of CI problem, then this will lead to occurrence of the fractional occupation numbers. We combine them with certain coefficients, and we end up with fractional occupation numbers, which will be given by these coefficients before the, the densities of the two ensemble components. So this is exactly what is been done at the level of the wave function theory in multi-configurational methods. Only now we don't use the wave function explicitly, and we only refer to the densities instead of the wave function. Here I simply work out these densities in terms of Kohn-Sham orbitals, and it's as you see, if we combine densities of two multi-electron configurations into this weighted sum, then we will have fractional occupations of some of the Kohn-Sham orbitals. And as a matter of fact, this representation immediately removes the problem with occurrence of holes below the Fermi level in these attempts to reconstruct the Kohn-Sham potential. The two orbitals, fractionally occupied orbitals, I should have shown them. I think they are shown with dotted arrows, but they are not very well visible, these dotted arrows. Anyway, these are fractionally occupied orbitals. One orbital, for example, occupied with Na electrons, the other with Nb electrons. They should be degenerate, but this is not degeneracy imposed by the symmetry. This is accidental degeneracy imposed by the ensemble representation. Whereas for the same physical density, one can try to apply single determinant representation of the non-interacting system. And then one not only obtains holes below the Fermi level, but also quite poor, poor accuracy for representing the exact density. So pure state V representable and ensemble V representable. So ensemble V representable in these numeric experiments, it leads to somewhat lower energy of the non-interacting particles, which agrees with the variational principle. So it should be the lower, the better. And also it provides much better fit of the exact density. So combined with the exact proof of ensemble representability, so multi-configurational representability of the density, so these numeric experiments, they provided sufficient proof of validity of ensemble representation, not only for, say, some kind of degenerate, symmetry degenerate systems, but for more general systems. And later it was kind of generalized, all these statements, mostly by Rob van Leuven, in a very simple scheme that for electronic systems where dynamic correlation dominates the correlation energy, single Kohn-Sham determinant is sufficient. And their standard Kohn-Sham methodology works quite well in these systems. However, as we have that non-dynamic correlation becomes important, as it becomes important in the electronic structure of certain systems, for example, dissociating molecules or bioradicals such as methylene, or symmetry forbidden reactions, so examples I have shown before. There we do need ensemble representation of the Kohn-Sham density. Right, so this is analogy with, say, wave function theory, where we associate multi-configurational wave functions with non-dynamic correlation. Here at the level of DFT, it will be ensemble representation. Right. Simple idea that immediately pops up. Well, let's use standard density functionals and insert in these standard density functionals ensemble density. So density with fractional occupation numbers. Right. But this idea would be not correct because if we now plug in density, ensemble density, into the energy expression uh, from the standard Kohn-Sham theory, so kinetic energy, non-interacting, well, okay, this term interaction with the external potential, it will remain the same. And problem arises with these two terms, classical Coulomb repulsion and exchange correlation energy. So it was demonstrated by Gross that if one uses ensemble representation in simple Kohn-Sham energy expression, that it will lead to some artificial terms which originate from interaction, classical Coulomb interaction between the ensemble components, which is absent in the exact formula that has been derived by Elliott-Lee. There should be only linear in ensemble energies. And there we have some quadratic contributions. Right, so therefore, density functional methodology with fractional occupation numbers may lead to wrong energies. It's not a proper way of building density functional for ensemble density. So proper way can be, again, obtained by invoking that idea of adiabatic connection. Let's imagine that we can switch off interaction between the electrons, setting this lambda constant to 0. So lambda scales electron-electron interaction, 1 over R12 term in the Hamiltonian. Well, in this case, of course, we will have non-interacting particles. I don't care at this moment about the external potential. I assume that it can always be found because I know that for ensemble density, it does exist. However, in this case, I have a system, ensemble system, where two fractionally occupied orbitals are degenerate. And they are occupied with some fractional number of electrons, Na and Nb, for each of them. What I can do now, let increase infinitesimally the lambda scaling constant, just by a tiny fraction, such that only electrons in the degenerate orbitals will feel this Coulomb repulsion, or I mean Coulomb repulsion between the electrons, and the electrons in core orbitals, there may be many more electrons in the core orbitals, which are non-degenerate, they will not feel this Coulomb repulsion. You see, when two orbitals or two states are degenerate, then any even infinitesimal coupling between them can lift the degeneracy, right? And that's what I would be interested in to construct the functional for ensemble density. Right, at this infinitesimal lambda, non-zero, but very small, I apply quasi-degenerate perturbation theory. I built a simple 2x2 secular problem. I solve it in the same way as I shown before, expressing energy of ensemble state through energies of individual ensemble components. So these are energies of individual ensemble components, and this is the coupling term. In the limit of strictly non-interacting electrons, this term will vanish, because this energy will become equal to that energy. Broken symmetry becomes equal to triplet if lambda is 0. And therefore, I end up with a strict ensemble representation of the energy of the non-interacting electrons. Then I take this energy expression, apply lambda integration, or integration with respect to electron-electron coupling strength, this constant, from 0 to 1. At the formal level, this can be done. And I end up with this simple energy expression where instead of energies of non-interacting particles at lambda near 0, at this value of lambda, I have density functional expressions of this same energies of the same configurations with lambda equals 1. So fully interacting particles, but I have now fractional orbital occupations of these two orbitals in the ensemble configuration. So from here to there, I go by lambda integration, and this can be done as is explained in a couple of the next slides, but I will not explain it in detail because it's too much, let's say, derivations. I will go to the next slide immediately. So I can obtain, for example, for the case of a strongly correlated system where I need to have ensemble representation for the density, I have the energy expressed in this way, right? However, for weak non-dynamic correlation or no non-dynamic correlation at all, I need to recover the same energy expression as in the case of standard Kohn-Sham theory. So, and the trick that I use in the derivation of my method was to interpolate between the two limits, limit of strong non-dynamic correlation, where both orbitals are, say, almost equally or exactly equally occupied, this limit, and limit of normal Kohn-Sham system, which is dominated by the dynamic electron correlation only. So as a matter of fact, for standard Kohn-Sham methodology, around these two occupation numbers of some frontier Kohn-Sham orbitals, let it be HOMO, let it be LUMO, highest occupied molecular orbital, lowest occupied molecular orbital in the standard description, I can obtain this expression with delta, which is almost the same as the exchange integral here, but only in front of it, there will be a linear term in the product of the occupation numbers of these two orbitals, and it will vanish in the case of Na2 and B0. But this one is square root of the two. So I interpolate, I introduce simple interpolating function, like it is shown here, between the two limits. And there are some kind of parameter delta was chosen to provide for smooth dependence of the variationally obtained occupation number, for example, one of the components of the ensemble, with respect to the magnitude of this term, delta. All right, so this is a non-empirical expression, maybe not exact, but all, our DFT is not exact either. And in the end, everything boils down to quite simple. For the case of two electrons in two active orbitals, this leads to ensemble with only two components. I have two quasi-degenerate, nearly degenerate orbitals A and B. All other orbitals are doubly occupied. I will have two configurations with doubly occupied orbital A with doubly occupied orbital B. They will make these contributions into the total density. So densities of these configurations will be combined with these weights. And I will end up with fractional occupations of frontier orbitals A and B. And the energy expression will have, again, two energies of the two ensemble components, which is the same, plus some term which describes coupling between the two components. So the formal level, at the level of, I mean, in the limit of non-interacting particles, the two become the same. So this term vanishes and the two become the same, very similar expressions with rho and E as it should be. But in the limit of, say, fully interacting particles, I will have some contributions from interaction, from coupling between these ensemble components. So then what I do, I optimize this energy variationally with respect to the orbitals, all these orbitals, not only active, but also core orbitals, and with respect to the fractional occupation numbers. So simultaneous optimization with respect to orbitals and fractional occupation numbers. So formality, I use OpenShell SCF for that case. For optimizing occupation numbers, well, it's easy problem. I eliminate one of them by constraint that I should have 2 electrons within the active subspace. And then I optimize the expression with respect to the orbitals under constraint of orbital orthonormality. And this leads to open shell methodology, which is quite tedious. I will not explain all of it. I will only mention that what you will see as after the SCF cycles, as the orbital energies are not exactly the orbital energies. They can be arbitrary, the diagonal elements. What is important that the off-diagonal elements become 0 at the convergence. So, and to obtain energies of orbitals, which we use to associate with the ionization potentials electron affinities, we can use a different trick. But the machinery, which is outlined here, is not really important. What's important is that this is open shell SCF methodology. And in this SCF methodology, when I impose this orthonormality constraint, Lagrangian constraint, the matrix of Lagrange multipliers, which can always be made diagonal in the case of closed shell Kohn-Sham systems, right? Standard Kohn-Sham single determinant, it cannot be made diagonal here. It should become symmetric, the matrix of Lagrange multipliers, but diagonal it cannot be made, because otherwise we would mix orbitals with different occupations. And this is one important difference between open shell SCF methodology and closed shell SCF methodology. So one is that the diagonal elements of the Fock operator are not exactly the same as in, or the interpretation is not exactly the same as in the closed shell and the case. And the other is that the off-diagonal Lagrangian multipliers, elements of the Fock matrix, in other words, they do not vanish strictly. So this is, say, Fock matrix, which is diagonalizable, but in reality, these Lagrangian multipliers...
Your Fock size is twice as big as normal Fock, right?
No, it's not twice as big. The dimension remains the same, only that I need to combine Fock operators of several electronic configurations when building it. So I build this Fock matrix from Fock matrices of individual electronic configurations, like shown here. Electronic configuration corresponding to W occupied orbital A, W occupied orbital B, and all these intermediates. Broken symmetry, AB, BA, and a high spin, both spins.
Oh, you sort of Fock is a linear combination then.
Right, yes, that's linear combination of, well, these and that are equal. Fock operators equal energy. I only write them for completeness, and this and that are also equal, and therefore I have 4 different Fock matrices to combine into one. So roughly speaking, this is 4 times more difficult than to calculate the Fock matrix of standard closed shell system.
So in your case, the interpolation you said, which is a kind of adiabatic connection, intermediate adiabatic connection, or variable adiabatic connection, right?
Yes, in some sense, one can say that. Yeah, this is, I want to interpolate between the limits of the, say, strong non-dynamic correlation, say maximally strong, which leads to equal occupation numbers of orbitals A and B, 1 and 1, and the limit of very weak or negligible non-dynamic correlation, where an A becomes 2 and B 0. So that was important for eliminating any, let's say, double counting. I can show it in some examples. So all this scheme was implemented in computer programs. In the very beginning, we used some now obscure code named CatPack. Later, I used Gaussian. Later, I did it in TerraCam, and now I did it in games.
Games.
Yeah. And, well, say applications are...
Say here, spin restricted here.
Right. Spin restriction is due to, well, orbitals for alpha and beta spins are the same. Space orbitals, I mean, special parts of the orbitals are the same. I didn't want, well, if I wanted to use, let's say, spin unrestricted, I would need to handle with, say, different orbitals for alpha and beta spins.
Yeah, that would be further more complicated, right? So.
It would be more complicated computationally, yes. I'm not sure that it would be really more complicated at the formal level, but in principle, it could be, well,
you just need more calculations for different orbital sets.
Yes, right. That would be 6 times cost of the UHF calculation, because I would need them all in that case, I suppose.
Yeah.
The cost calculation of the calculation would increase, simply speaking.
Okay.
So, and I can in the following show some applications for the ground state.
By the way, sorry, we need to limit the time. So
yeah, we have already half an hour.
So maybe we should finish it soon.
Yeah. I will. I think that I have maybe about 10 slides remaining, which are quite simple to show.
And then
so one of interesting
10 more is too much. I think that Anna wants to talk, give a question.
Right.
Yes, actually, I didn't understand fully. So you for the particular system, you calculate the this f function. So that interpolation function. Yeah, and for each particular, it is different for each particular system. Yes.
No. It's all the same for all systems.
You just obtain it for one function that's obtained for and use it for well, I see delta is 0.4. Yeah, it is. Yeah, you find it for. It depends on what. Your correlation.
It's shown in this graph. Let me tell you. If I set delta to 0, then there will be no unique solution for the given energy difference between the well, this parameter here, capital delta, abscissa axis, characterizes energy difference between the two electronic configurations. W occupied A, W occupied B orbital, divided by the coupling term. So this is the same parameter as in inverted parameter as in the perturbation theory, right? So 0 would correspond to say degenerate configurations, and non-zero would correspond to non-degenerate. So they are negative, these parameters, as a matter of fact. All right. If I set this small delta to 0, I obtain non-unique solutions for the occupation number of fractional occupation number of the orbitals, because there will be an artificial solution corresponding to some intermediate, and there will be very non-smooth dependence of this occupation number. In fact, both occupation numbers on these.
So what is the reason you choose 0.4? Is that
if I use with delta 0.1, it's smoother and it's unique solutions, but it's not really smooth. There is kind of kink at this point. Delta, if I gradually increase delta any further, I see that starting from delta approximately 0.4, I increase them in fixed steps, 0.1. 0.2, 0.3 I don't show because they are very close, but I see that they gradually converge, and if I go beyond delta 0.4, they all remain these curves, the dependence of variationally optimized fractional occupation number on this parameter, which is the most important for the magnitude of correlation. I see that they all converge to the same dependence. You can probably delta 0.5 is very indistinguishable from delta 0.4. 0.6 would be also very close. So they converge.
Okay, but do you obtain this number from some particular computation or for some particular system, or you?
No, this is not for any particular system, because
not for
this
any particular
parameter is, you see, when I optimize that, all right, where did I put optimization formalism? All right, it doesn't matter. I can optimize by Newton-Raphson method. When I know energies of all these components of the ensemble, right? I optimize for.
So it is in common case. It is just a theory, yes. And you did not apply any specific DFT correlation potential, yeah. DFT functional, yeah. It is for any functional, yes.
Right. I did not apply any because I think I was testing my Newton-Raphson optimizer for these fractional orbital occupations. And I found out that the value of this depends on this parameter, capital delta. Well, and then knowing this, it's quite nonlinear dependence, in fact. But knowing this, I can find always this orbital occupation number, fractional occupation number. And as a matter of fact, that Newton-Raphson procedure, it would converge to say non-unique solution if I set small delta to 0, to a non-smooth curve, non-smooth solution if I set too small delta. But it starts rapidly converging to one and the same dependence, starting approximately from delta equals 0.4. I did not try to find any, say, refined value of these. Simply.
So, and it is affect. It is affect only Coulomb interactions. Yes.
Right. This is largely defined by these parameters or ratio of the average of the, I mean, difference of the two energies and the coupling term.
Okay, so nothing else. This is good point to stop. Okay, so we'll continue from here. Yeah, okay, Pavel, yeah. Pavel, you have a question?
Actually, I have a lot of questions.
Okay. One question.
Right away.
One question. Actually, I'm going to just make a talk about the quantum materials next Monday, actually. And I suppose that the ensemble DFT may be the best method to apply for them. And I'm going to discuss it. Actually, it's incredibly important for quantum materials. No way to model such sort of materials by using just ordinary, regular DFT or something like this. I'm going to talk about it next
one day. Yeah, we were looking for it.
Incredibly important.
Yeah.
Actually, I promise you that for me it will take not more than 60 minutes.
Okay, you don't have to, but okay, so maybe I wasn't really properly preparing Michael's talks because I didn't know where to stop. So, but then anyway, I have to stop. Saima, you recorded everything, right?
One last slide I would like to show before we stop.
All right.
About that interpolating function, that it is important to correctly describe the energy at the, say, equilibrium conformation. For example, a hydrogen molecule, as you see, the dissociation curve obtained from REKS 2,2 and from standard Kohn-Sham, they go to different dissociation limits. Of course, REKS goes to proper dissociation limit, -1 atomic unit, Hartree. But near the equilibrium geometry, both curves are the same, and the energies from REKS and from standard single reference DFT are also the same. And here, the electronic structure is dominated by single electronic configuration and mostly dynamic correlation. So this means that REKS does not introduce any, say, any extra contribution into the standard Kohn-Sham description, provided that Kohn-Sham description is valid. And the same I observe also for twisting about the double bond in ethylene molecule, where at planar conformation, I obtain the same energy as from the standard single reference Kohn-Sham, although at 90 degrees twisted.
Yeah. Okay, so we'll talk about tomorrow, all right?
That will be tomorrow.
Yeah. That will
and
be...
also excited states will be.
Yeah. Okay. That will
Yes.
So, yeah, I didn't know that Dr. Filatov wants to talk this much of material, but I think that this is very useful for us. This is a good time to understand what he's been thinking for such a long time, and this is really a beautiful theories. I guess we will have another meeting tomorrow and the day after tomorrow, all for Michael. Michael will talk about. You will have 2 more days. So I hope that is sufficient. But also, Saima is recording all of this. So Saima is going to upload to this YouTube. So you can, if you couldn't understand some part, and you can still watch again, and you could give questions to the Michael again. So Saima, when you upload it, please cut into some small pieces rather than the whole entire. Can you do?
Yeah, maybe like 1 hour. It's almost like
30 minutes.
It's 2.5 hours almost.
Yeah, so
Right.
30 minutes. Yeah, I will divide it into.
We have many contents.
Yeah.
Our YouTube channel will be popular.
Yeah.
Okay, great. Okay. So tomorrow we'll start at 3 again, and now this is a very, very important. The Pavel, we haven't really discussed about the restaurant and also the when we do it, right? So what do you think? Should we delay or should we postpone maybe?
Let's delay.
Yeah, because we haven't discussed it, right?
Yeah.
So we will talk about having dinner together. So we will let you know. Okay, great. So other than that, Hiroya, do you want your baby is sleeping now? No, okay.
She's sleeping.
Okay, great. That's great. Okay. Any other?
I have one question.
You have a question? No, tomorrow, please.
I would like to know.
Someone has a kids too. Oh, sorry, Hiroya. Just okay. You have 30 seconds to talk.
Okay, I have some question. I would like to know how to get to the gradient for REKS.
Okay, that is for tomorrow. That'll be tomorrow. Gradient, right?
Gradient for the energy.
Yeah, gradient for energy.
Yeah, that'll be for. Wait, Michael, wait.
Simple answer can be given also.
No. That'll be tomorrow. Okay,
because
so
for
you're
this
coming back.
REKS 2.2 single state method, the gradient of the energy, because the energy is variational, then the gradient of the energy can be obtained with the standard Poolai energy expression, gradient expression.
Okay, so we will talk about more because I also have questions for that. So, oh, by the way, let's